All right, so AP Physics, we are getting towards the end here. Tomorrow, I'm going to make a video specifically that's just on like all the AP College stuff you need to know about the exam. You should have been receiving emails from AP College Board at this point. If you're not, you need to make sure that you go into your AP College Board account and check to make sure that your address and your email and all that stuff is set up properly. And if not, I sent a little video in the web page last week. I didn't send it. I made a little link that kind of explains some of that stuff and what you need to go through and do. So if you're ever having a hard time receiving communication from AP College Board about our test and any other test you might be taking, there's a little video again that I posted that I think would do a good job helping you out with that. That not being the point, let's talk about kinematics. Start from the top. Kinematics is the first subject that we covered at the beginning of the year, and I'm going to kind of do a brief overview. I'm going to run through everything that I think that you need to know. It's more about remembering kind of keywords and phrases in terms of problems. Feel free to go back and look at College Board stuff. You know you have a lot of multiple choice examples there. You know that I gave you those study guides before we went on spring break. So if you have those and you want to ask questions about them, you can always look at that. But in terms of overall stuff, that's what I'm going to be covering in this video. I don't know how long this will take me. No idea to predict it ahead of time. So just know that I'm going to kind of cover everything kind of as I go, from the top. So kinematics. Remember that kinematics is really the study of motion. We're not talking about what causes this motion. We're not talking about what stops this motion, that kind of stuff. We're just talking about the actual motion itself. So we're not talking about forces or momentum or the energy that goes into doing it. That's all the stuff that comes from this section, which is why this one's first. So remember that we covered motion in both one dimension and in two dimensions. So motion in one dimension, as we remember, is just in one straight line. So it's just going left and right or up and down. The main thing to remember is that if we're talking about something that is moving up and down, we do need to remember that gravity does affect it, right? So that's just a thing to remember. It's going to come up with every subject that we cover here, except for probably electronics, which is not on this test, right? Where gravity does have an effect, where we do have to worry about at what direction or at what point we're doing this. But not anything we have to worry about right now. So looking at motion from the very beginning, we know that motion is the most easily defined as something's change in its position, right? Something is somewhere and then it goes somewhere else. And in talking about that, we know that that means that there has to be two components that go along with that motion, right? Motion absolutely has to have two pieces. And so we know that they are X or Y, this thing called displacement, and a time interval. I'm writing this down. Cool. So we know we have to have these things. We must have a displacement. We must move away from our origin. And we know that motion takes time. There's literally no amount of motion in the universe that we know of yet that doesn't take any time. Even most theoretical, really quick motion still takes time, right? In Star Trek, they have teleporters, but even those teleporters literally take a moment of time to pass that information for them to materialize. Even in the Marvel movies, you have Doctor Strange. He uses this ring, but in order for him to pass through the portal, he doesn't do so instantaneously, right? His legs and then his body to go through it. So that literally also takes time. So even really fast modes of measurement or of travel motion still require these things, right? We have to have some motion. Now we use X obviously for any horizontal motion and Y for any vertical motion. So in a lot of our formula, you're going to see a lot of things will default to X, but you remember that again, that Y just means up or down. So we have to have this thing, this displacement. Now displacement does require an origin, right? So we must go from where I started to another place. If I were to leave my origin and then go some other place and then come back and somebody were to look at that entire time interval, I would actually have no displacement and then therefore I would have no velocity at any given point. Now, again, that's the key difference between distance and displacement. Displacement is a reference to that origin. Now, that's looking at it in terms of time intervals. Remember that we can split these time intervals up and it'll give us different pieces of information. For instance, let's say that you were traveling across country and you said, well, I traveled 50 miles in 2 hours. And I go, oh, cool. So you did 25 miles per hour the entire time. Well, that's not necessarily true. We know that that's just looking at it as an entire time interval. There's probably time periods where you were stopped, where you would have 0 miles per hour as your speed, or 0, any other measurement, meters per second, whatever it might be. And we know that that, again, is not indicative of what we're calling this average velocity. And that's kind of a big thing we're taking a look at is this differences between these things called average, which takes place over a long time interval, or these things that are called instantaneous, or what is happening exactly right now. Yeah, so instantaneous would be like if you're driving down the road and you look at your speedometer, the speedometer tells you what is your instantaneous speed, right? Doesn't tell you velocity because it doesn't tell you direction, although some cars do. Yeah, and remember that that's a big thing for displacement. Displacement is the first of what we call our vector numbers, right? Remember these two terms. We have vector and we have scalar, right? Vector is just any number where direction is really important. We give that direction by a positive or a negative, right? Not always. If you do north or south, that's a direction that would give you vector. But even north or south traditionally are illustrated by a plus, which is up, which is north, and then a minus, which is down, which is south. Does it have to be that way? No, but you have your own definition. And then you have these scalar numbers, and they don't have direction as a function or a focus, right? So again, our first vector number is this displacement. So you see I have this little graph. So let's say that this was your origin, right? So at our origin, if I were to go anywhere over here, my displacement is going to be positive because I have a positive y and I have a positive x, right? Anything over here and everything's going to be negative because I have a negative x and a negative y. And then obviously, your other quadrants are going to change based on that, right? Here, my y is positive, but my x is negative. And here, my x is positive, but my y is negative. But all of those numbers are going to give me a vector number, right? A number where I can use positive or negative to indicate that direction. And that's all they represent. I can make it mean whatever I want. So let's say, for instance, I'm looking at a graph, and that graph represents what we're going to call a position time graph, right? So how does my position x, let's actually draw an x. How does my position x change? And that looks more like, whatever, this probably more similar to class than I can realize. How does my position change over time? So let's say that I'm walking down a street, and that this is going to represent both 0 seconds here and 0 meters away from an origin. But let's say that I'm going towards my house. My house lies east of me. And so let's say that I'm going to say that east is actually in my quote-unquote negative direction, and that means that west is my quote-unquote positive direction. So I'm going to start away from my home, right? The distance is away from my home, and I'm going to go towards my home over this amount of time. So this distance represents the time it took. This represents the actual, like, in meters distance, right? In fact, we would even indicate that meters, and this would probably be seconds. And that is going to tell me, again, how long does it take for me to go from where I'm away from my house toward my house, and I defined west as the positive direction, right? And if I were to take the slope of this line, that slope is going to give me the velocity, right? Because slope tells me what's the rate of change of this thing. Well, the rate of change is how many meters am I going per second, which is what velocity is, right? Another way of saying that is what's my rise over my run, and my rise, my up and down, is meters, right? And my run is seconds, and so therefore the slope of this graph, a position time graph, is going to be meters per second. And so that's the first thing where we can see those things are related, and we can see that velocity also is a vector number, because that number I just gave you is a negative slope, right? That number is going to be pointed back down that direction, right? It's not going up, right? That would be a positive slope. And so we could see there that a velocity is a negative quantity, or oh my God, I'm not going to read this entire video just to fix that for a brain fart. You're probably used to me doing brain farts. It is a vector quantity. Velocity is a vector quantity, which makes it different than speed. You will see those things overlap a lot, especially in the way that they refer to them in problems, but they're not interchangeable, but they can be given the situation, right? Cool. So that gives us to that definition, right? We know that this displacement, right? This delta x is my displacement, technically. Technically, this delta x is my displacement because x represents my position, and of course, it means my horizontal position. If I have both, I'll have an x and a y. And so a change in my position is my displacement. So what we know is that in order for me to have any sort of movement, I have a change in position that takes me a certain time interval to complete. So that gives us our first one. That's average velocity. My average velocity, and I know that's shining off of that, but my average velocity is a change in position over time. Now again, does that mean that I can't use y there? No, I'm going to go up and down, so I could definitely use y. It all depends on the context. So that is our first formula. That formula can be used for a lot of different things. It means that if I want to find out what was my change in position over a given period of time, then my velocity times the time interval is going to give me that. Now that's my average velocity over times that time interval. And that's saying that, like, what would be over the last 5 minutes, what was my average speed, right? And you would calculate that by calculating the distance and dividing the time out. You see how they're all related? Now that we do know that speeds can change, right? Right now we're talking about speeds that don't change. So let's go with that. So talking about speeds that don't change, we can take this to figure out either where did I start or how far did I travel, right? Or even where am I now? So given all of that, you can see delta x. Remember, delta x or delta of anything is that final version or the current version minus the original version, and that'll give me what my change is. You'll also see this as xf minus xi. The test tends to do these knots. X, my current x, minus my not or my x at the original time. Now that's the same thing as saying this xf minus xi. It's up to you to remember that. It's up to you to make sure you have some sense. Can you use this? Yeah, I think you could totally use that. I don't think they're going to have any problem. So now we have this. Delta x is x minus x up. So given all of those pieces of information, we have another formula. And that formula says, okay, so if delta x is x minus x naught, which is equal to v delta t, right? Bam. Then that means that my current position can be found by calculating that v delta t and adding my original position. Hey, that's where I am now, right? Or I can find any one of these other pieces, right? I can also use this to solve for what is my original position, right? So taking this equation up here, we can also say my original position is equal to v delta t. And then you're going to go minus this x. Okay. And that's actually going to be, I'm trying to do the algebra sideways here, so I apologize. So we have, I move this to the other side by I'm subtracting it from both sides. It's positive here, so I'm going to subtract it from both sides. And then I have this negative over here. And what we're going to have is x equals my original, or my current x, I'm sorry, my original x is equal to my current x minus b delta t. I'm going to do this not sideways because that's what's screwing me up. I apologize. All right, so let me just do it here. Cool. So x minus x naught is equal to v. You probably already have this, and I don't care about because I can't see your face, so I'm just going to go ahead and do it. So negative x naught is equal to v delta t plus or minus my current x. So then negative x naught is equal to negative v delta t plus my current x, which means that I want to go x naught is equal to x minus v delta t. Okay, cool. So we go through this. This is, again, that same formula. My change in position is equal to these things. And so then I'm going to move, what's my current x, to the other side. And I get this thing that says, oh, my negative starting position is the distance I covered in that time period minus where I ended up. And you go, okay, cool. But that's not what we want. What we want is a positive version of this. What's the positive version of where I started? Well, where I started is equal to the following. It is my current position minus the distance I covered in the elapsed time. I apologize for that. And so again, that's what you're going to get down here, is that my original position, right, is equal to my current position minus the distance that I traveled in that amount of elapsed time. And that makes sense, right? So there you go. That's pretty straightforward stuff. And so that covers all of your displacement. Cool. And that's displacement and velocity and how they're related. Now again, we know that our velocity can change. And when our velocity does change, we call that acceleration. Now, acceleration is quite literally that, right? So acceleration is quite literally, acceleration is equal to a change in velocity over a change in time, right? Bam. Acceleration is equal to a change in velocity over a change in time. So if I speed up or I slow down, we know that I am having a change in my velocity and therefore I have an acceleration. Cool. The other thing to make sure you remember is that since velocity is a vector number, that changes in direction also qualify as changes in velocity. So when I turn, which we talked about in circular motion, that means that I am experiencing a change in velocity. Awesome. So that leads us to a fair number of equations, and I'm going to write those equations down. So I'm going to write down these equations that gives us acceleration is equal to delta v over delta t, which we just talked about, which leads me to my change in velocity is equal to acceleration times time, which gives me bf at plus vi. Cool. So we have these equations, and they're pretty easy to use and pretty easy to derive. They're just different versions of this equation. My acceleration is a change in velocity over a change in time, which means that if I just want to know how much did my velocity change over a given period of time, I take the acceleration times the amount of time that the acceleration was occurring. And then it's just splitting out what does my delta v means. We go, okay, well, I can figure out what my initial or my final velocity is if I know what my change in velocity was and what my initial velocity was. Cool. And the same thing is true. If I wanted to find my initial velocity, all I would have to do is algebraically go back and solve for these parts. And I would just erase a bit of that. That's all that tells us, right? It just tells us that we can track these things. And they're just iterations of that idea, that an acceleration is a change in velocity over a change in time. All right. So that gives us the ability to now figure out how much distance we cover with an acceleration, right? So we just have, well, how much distance did we cover without an acceleration, right? And that was that my delta x is equal to v delta t. How much distance did I cover without an acceleration? I'm going to be covering this distance at a constant rate, right? And so because I'm covering that distance at a constant rate, I don't really have to worry about any of those changes. But now all of a sudden, let's say I do speed up and slow down. We have a couple of different formulas that help us figure that stuff out. So the first one you're going to see here on the formula sheet is going to be this one. X is equal to xo plus v. Let's see how they wrote this. xo. Oh, I'm giving myself enough space. X is equal to xo plus bxo t plus 1/2. Oh my God, I'm sorry. X is equal to xo plus bxo t plus 1/2 axt squared. Okay. Bam. Cool. So this is my current position given all of these factors. This is actually the same formula as saying delta x is equal to v delta t, but being like, well, actually, since I don't have an average velocity, can I replace this stuff with something that gives me acceleration? You'll see that we have this added term that includes the change in my velocity, right? So rather than saying, oh, I have the same velocity the entire time, we have this velocity originally was going times time, and this added term that means what was my acceleration. And again, this is just splitting that delta x out and then moving the x over to the other side. So that's what this gives me, right? This gives me literally, where am I at given these factors, right? Given where did I start, what was my starting position, x naught, my starting velocity, the time I traveled, what was my acceleration, and again, the time that I traveled squared, right? So we could actually even move this over. If we wanted to just know what was my change in position, I could do delta x is equal to vxo t plus 1/2 axt squared. Right. Cool. So I could even do that, and that would just tell me what was my change in position. It wouldn't tell me where I was at, which is what this does. It would tell me how far I had traveled. And so having given that, again, let's say that I start off with something that's falling. So this section here is actually going to go away. Why? Well, because my initial velocity is going to be 0. Now, of course, this would be y, so don't forget, this would be y. But let's say that. Let's do that, okay? So my y is equal to my original y starting position plus v y o t plus 1/2 ay t squared. Right, so let's say that something was falling, and that would be able to give us either where do I end up, right? Where did I start falling? Or combination of those two things will give me how far did I fall, right? So let's say that I want to do that, combination of those two things. I'm going to subtract my y over here, and I'm going to get delta y, and now that is, how far did I fall? Well, when I'm falling, right, so let's go v y o t plus 1/2 ayt squared. Cool. So when I'm falling, I won't have this term because when I stopped or when I started, I wasn't originally moving, right? So let's say something is dropping. So I'm going to get this delta y is equal to 1/2 ayt squared. And then it brings us to an idea that is super, super, super important, which is that this, when we're falling, ay is g, and g is my acceleration due to gravity. And that gives me that g is equal to 9.8 meters per second squared. Now, of course, when we're talking about down, that should be negative. Cool. All right. So again, that's how we use that formula. That formula gives us position given time and acceleration, right? Something is accelerating and they gave us the time. And sometimes we're going to use that to solve for the time. Remember that for all of these variables, all of these equations, all of this, you can actually go ahead and solve for any of the things that are in there, given that you have the other pieces. Sometimes we're going to have to take parts of this, kind of evaluate them and say, can I set t equal to all of these other terms? And then once I've set t all of these equal terms, go to a different equation that has t and pump it in there. But again, I doubt you'll see a lot of that on the FRQ for these tests. Make sure you take a look, obviously, at the FRQ for this week. And that brings us to what I think is probably your favorite equation, which is this equation that we've been calling braking distance, which is accurate. So Vx squared is equal to Vxo squared plus 2ax delta x. Now, I'm going to write this a couple different ways because they're going to do it differently on your formula sheet. Cool. So they're going to write it this way on your formula sheet, and that's just because they're going to take that delta x and they're going to spread it out. So they're going to do x minus xo. Again, x, my current position or my final position, minus x naught, and x naught is what is my original position. What is my position when no time has passed during my observations? Cool. So we've been using this for braking distance. You guys absolutely love this formula. It's pretty straightforward. If I have a starting speed and a slowdown speed and the distance it takes, I can find the acceleration. If I have the starting speed, a slowdown speed, and I have the acceleration, I can find out how long it takes for me to cover that distance and all that kind of stuff. Now, of course, all of these things assume that my acceleration is constant because we don't really deal with changing acceleration in this class. That doesn't mean that things don't change their acceleration. You know that they can. But again, most of our things assume constant acceleration. So having gone over all of that, we now have these five equations that you really need to make sure that you can keep track of. And they are basically as simple as follows. We have cool. All right. This formula at the bottom, technically the same formula as up at the top, but we've just solved for a particular, or excuse me, as the acceleration formula. We've just solved for a particular part that was at the top. Yeah. So that's pretty much all the things that you need to know in order to solve for everything in this particular section. We did have some other formulas, but they were derived from these formulas, right? We did have some other pieces, but they just came from these parts. So as long as you can identify all of these parts when you're working on the exam, you'll be able to work your way through everything. It's just those concepts, right? If I am speeding up or slowing down, I have an acceleration. If I am moving anywhere, it takes place over time, and therefore I have a velocity. I could be going at the same velocity, but if I am moving from one place to another, I have some velocity, right? Yeah, I mean, those are really the only concepts I would say to make sure that you understand. Free fall, we have this acceleration g is equal to 9.8 meters per second squared. We know when we throw something up in the air, it has to stop. At the moment that it stops, it has no velocity, right? When I drop something, it starts with no velocity. These are things that we need to remember, but hopefully are almost like second nature to you. So this is a pretty long video. If you have any additional questions or things that you need to ask me about, you just let me know. That is an overall view of kinematics, and that is how those things are related. Oh, you know what? One last thing. I don't know if it'll come up or not, but one last thing as relates to kinematics, right? So projectile motion, or motion in 2 dimensions. The main thing is just to remember that when I have motion in 2 dimensions, right? So let's say that I have the ground, and I'm going to throw something off of that ground. I can take every pieces of those motion. I can take the distance. I can take the velocity. I can take the acceleration. I can take all of those pieces, and rather than have them be in 2 dimensions, I can have them be in an x direction and in a y direction. And why would I split them? Because they're easier to handle and they don't interact with each other. So the main thing, realizing that again, I can take any 2-dimensional and I can put it into being 2 one-dimensional pieces. So I have this piece, which we're going to call my original vector A, and I can actually find these pieces AY and this piece AX. And I would do that because these two sides don't really interact with each other, especially as it pertains to like velocity and things like that. And so I can split them up, and it makes it really easy for me. And I can do that by just using some trig functions, right? They have all the trig functions on the formula sheet for you. That doesn't mean that you have them memorized or that you know how they work. So just go make sure you run through them. But again, let's say I wanted to find this side. Well, this is my adjacent side. So we know that cosine is associated with that. Take my original vector, do the cosine of the angle given. And this is the angle theta. And it'll give me this x side. And that means that if I take the original vector, do the sine, of the angle given. It'll give me the y side. So there you go. That's a lot of stuff to kind of throw down in a video. When you go through and take a look at the FRQ this week, if there are additional pieces of information you need to go along with that, you just let me know. And again, I'll be recording these videos as we go along. So just let me know what you need, what you don't need. Okay? Appreciate it.